Countdown, 4, 3, 2, 1. This 1 minute statement. This DVD is not high quality, but should suffice to make my important points. I'll take care of moving the pointer and scrolling the pages, but you may have to adjust the sound volume of your DVD player or computer sound volume, and maybe reducing the size of your screen a lot so that the main lines show up dark and focused, and maybe drag your timer bar back to the 0-second start position. Some of the major sections of my sphere patterns also appear on old tablets in Japanese Shinto shrines and Buddhist temples. My page 2 equivalent and some additional details appear in old prominent publication, Journal of Chemical Information and Computer Science, volume 35, 1995. Pardon any of my verbal slips and occasional 10-second pauses. Lesson view. On this first page, please note the symmetrical, very simple sphere patterns near the top of the page and near the middle of the page. There is a small centered sphere in each sketch and 3 or 4 medium-sized spheres shown around that, and one big sphere around the 3 or 4 medium-sized spheres. Let's first talk about the sketch at the top of the page and note that the sphere volume of each of the 3 medium-sized spheres compared to the volume of the much smaller single-centered sphere, and each of those 3 medium-sized spheres has a volume of 270.1 times that small centered sphere, a 270.1 to 1 volume ratio. Thus, abstract geometric patterns lead to abstract volume ratios, and there exists in the real world large mass particles like the proton and fairly large particle masses like the average pion particle, and much smaller mass particles like the electron. And to our surprise, for example, the mass ratio of the average pion particle to the small mass electron particle is also a 270.1 to 1 ratio. So among various prominent real particles in this world, there often occurs, like just shown, real mass ratios that nearly equal the volume ratios in abstract geometric patterns. That's the major theme of this talk. And the one large sphere around the 3 medium-sized spheres compared to the small centered sphere, that is, the largest sphere to the smallest sphere, is a 2702 to 1 volume ratio. We'll say more about that later and other ratios also. But let's now talk about the sketch near the middle of the page, where a fairly large sphere surrounds and touches 4 medium-sized spheres, and those 4 surround and touch a small centered sphere. The volume of that fairly large outer sphere compared to the small centered sphere is a volume ratio of 970.00 to 1. And perhaps to our surprise again, that abstract volume ratio, 970.00 to 1, almost exactly matches the mass ratio of 2 very important prominent particles in the world. The average kaon particle mass to the small electron mass, a ratio of 970.0 to 1 also. Now in the sketch near the top of the page, we use a simple triangular array to help lay out the pattern there. And near the middle of the page, we use a simple tetrahedral array to help lay out the pattern there. Both patterns, the one creating the largest sphere to the smallest near the top of the page, and the one near the middle of the page that created the fairly large sphere to the smallest, are such nice basic patterns we can hardly choose a favorite. So let's just average the two volumes together, the 2702 to 1 ratio and the 970 to 1 ratio, and draw a sphere volume near the bottom of the page equal to those patterns averaged together. That average volume ratio comes to 1836.0021 and is represented by the big sphere at the bottom of the page relative to the very small sphere shown just above it. And perhaps to our surprise, that abstract volume ratio almost exactly equals the mass of a proton particle compared to the mass of a much smaller electron, 1836.15 to 1 ratio. So by averaging together the volumes of perhaps the two most basic sphere patterns in geometry, we almost exactly match the mass ratio, 1836.15 to 1, of the two most prominent particles in the universe, the proton and the electron. And since the neutron particle is perhaps the third most prominent particle and is only a few electrons more massive than its partner, the proton, we nearly matched its mass ratio to relative to the electron. Now we moved on to page 2. Scrollers, please scroll down to the next frame, and page clickers, please click back to the index and click topic adjacent page 2.
I take care of that.
Here we see different patterns from the ones viewed previously. In the sketch near the top of the page, the pattern is generated from 3 small loose packed spheres near the center of the pattern touching the other spheres. But in the lower sketch, the pattern is generated from 3 close packed small spheres, not loose packed, that are touching the others. Even though the patterns are differently constructed than on the previous page, they remarkably lead to the same big sphere sizes relative to each small sphere. The same largest to smallest sphere ratio, 2702 to 1, arises in the upper sketch and 970 to 1 in the lower sketch. So the average is again equal to the previous 1836.00 to 1 ratio, again almost matching the proton to electron mass ratio. And that illustrates another major theme of the booklet. Suppose there are a few or quite a few different geometric sphere patterns that nevertheless create or almost duplicate the same volume ratio as others. That increases the chance of their existing in the real world prominent particles with mass ratios that match or nearly match those abstract geometric ratios. This talk is not long enough to cover all the prominent particle mass ratios nor the average of them and all the nice pattern volume ratios that they nearly match, and not long enough to even cover the whole booklet, nor does the booklet cover all the somewhat less prominent particles and patterns. Nor do my major points answer all askable questions. But let me make a few slightly technical comments, which non-specialists may just regard as optional. There are no standard particles, that is, compact mass particles, in the mass range of greater than 1 electron mass, but smaller than 200 electron masses. The reason is likely this. Even if such compact small particles could start to spin at the velocity of light, they still could not develop much angular momentum. They probably couldn't develop even as much as something called a Planck's bar constant amount of angular momentum. That likely relates to Heisenberg's uncertainty principle. In this case, not only would certain aspects of the weak little particle be hard to measure accurately, the particle seems to find it too difficult to exist at all. But the electron, when outside a nucleus and loose, is a very spread out particle, perhaps like a donut or puffball, and not like other more compact particles. If it spins at nearly the velocity of light, it easily therefore develops the sufficient angular momentum and thus likely more support for its stability. Now please skip the next 3 frames and land on the 6th frame, or return to the index and click page 6 topic. That should take you to page 6 or frame 6, where we talk about the muon particle. In previous sketches, we began with one or more very small electron spheres and drew larger spheres around them, and sometimes still larger spheres around those. And thus we studied spheres and particles of much greater mass than the electron. Now we sort of reverse the approach, and we start with 2 large proton-sized spheres, each representing 1836.15 electron masses. Now, using medium-sized spheres, we draw 2 equal spheres inside the proton near the top of the page, and 3 equal medium-sized spheres inside the proton near the bottom of the page. And as shown toward the left-hand side of the page, we average the volumes of one medium-sized sphere from the upper sketch with 1 medium-sized sphere from the lower sketch. And that averaging gives us 206.54 electrons, as shown at the left of the page. And perhaps not so surprising anymore, that nearly matches the mass of an extremely prominent particle in the real world, the muon particle, with a mass of 206.77 electrons. We now scroll down to the next frame, or click page 7. There we will talk about the major lambda hyperon particle. Near the bottom of the page, we see one large sphere that surrounds 4 medium-sized spheres, and those medium-sized spheres are close packed around 4 small electron spheres, similarly packed. The volume ratio thus resulting, the big sphere to each of the 4 small ones, is 2180.19 to 1. The sketch above it, although differently built, gives the same ratio, biggest to each small sphere. And that ratio is very close to the major lambda hyperon particle mass compared to the electrons, 2183.34 to 1. That lambda hyperon is the most prominent particle among particles of greater mass than the neutron, and was among the earlier particles discovered. Regretfully, there is not enough time to give more details about it and other related things. So let's skip the next frame or page and instead go to the 9th frame or page 9. The pattern at the top of the page you've seen earlier. It generated the volume of 2702 to 1, or a mass of 2702 electrons. And the cross-sectional sketch below it, although built differently, creates the same 2702 electron mass. That cross-sectional sketch consists of one big sphere around 8, and those 8 around a medium-sized sphere, and that around 8 rather small spheres, and those around one small centered electron sphere. We saw earlier how 2702 to 1 volume ratio, when averaged with the 970 to 1 other ratio pattern, created a 1836 electron mass estimate for the proton's mass, a close estimate indeed. But the 2702 electron mass does one more good thing. It also is very close to an important mass, 2706 electrons. That is something called a major mass resonance with equivalent MC squared resonance energy. For the specialists, when a small mass particle is thrown against a massive particle target, a greater amount of scattering occurs for a special total mass value, the so-called resonance value. That scattering is greater than if a somewhat lesser amount of total mass or a somewhat greater amount of total mass was involved. And that 2706 electron mass value is known as the lowest resonance mass or energy of the energized sigma hyperon particle. But now let's skip the next 3 frames or 3 pages and land instead on the 13th frame or page 13. Stretched out across the lower section of that page, we see a very large cross-sectional sketch. It illustrates one large sphere around 6 medium-sized spheres, some of which are partly hidden, but those 6 spheres are close packed around 8 smaller spheres, which surround one centered small sphere. If the volume of that centered small sphere represents 1 electron mass, then the very large sphere represents a particle equaling 2995.03 electron masses. That is very near a major resonance particle equaling 2997.7 electron masses, or its equivalent amount of MC squared resonance energy. Specialists may note that major resonance is known as the lowest resonance mass or equivalent energy of the energized chi hyperon particle. We commented previously about resonance, but now let me comment about simple ideal sphere patterns. Among ideal Platonic layouts, there are solids with 6 points and 8 faces, and 8 points and 6 faces. They are complementary.
Are duals.
And the volume ratio of our one big sphere around the one single centered sphere would not change if the internal layering between them was 8 spheres around 6 instead of 6 around 8 spheres. In either case, the fitting and symmetry would also be perfect. Let's skip the next frame or page and instead go to the 15th frame or page 15. Here we see major patterns and sphere volume ratios formed by using the most advanced Platonic layouts. The main sketch shows one big sphere around 12 medium-sized spheres, which are close packed around a bunch of 20 small spheres that are somewhat hidden and therefore brought out and shown at the top of the page, the sketch at the top of the page. And those 20 spheres surround one dark sphere, and we'll imagine that dark core sphere as a reference proton volume instead of an electron, because it is bigger than the small spheres touching it. Comparing the main big outer sphere volume to the inner proton core sphere volume gives us a volume ratio of 133.65 to 1, which seems to also be the ratio of the Higgs particle mass compared to the proton's mass within experimental error. That same outer sphere to core sphere ratio would result, regardless of whether the sphere layering between them was 12 around 20 or 20 around 12. They are complementary.
Are duals.
So perhaps we can say this: the final target of Euclid's 8 books, and the pattern that Plato thought God used to make the heavens, also helped us here to match the so-called God particle mass, the Higgs mass, a major target of the mainstream's standard model of particle physics. That ends my presentation. Thanks.